You send a message, right? And you just assume it gets there. But how? Well, it's not magic. It's this incredible, invisible journey. And today, we're going to break down what really happens to your data the second you hit send. All right, let's get into it. No, really, take a second. You tap your screen, and boom, that information is halfway across the planet. How on earth does it survive that trip? What kind of dangers is it facing out there? That's the big question, and we're going to answer it right now. So, let's follow one little piece of data on its adventure. Our hero for today? Just a simple hello. Its mission is to get from you to your friend. But see, the path it takes, it's not some perfect, clean digital superhighway. Nope. It's the messy, chaotic, real world, a place that is just buzzing with electronic noise and interference. And this right here, this shows the core problem perfectly. On the left, you've got the plan. That's our data in its perfect, clean, digital form. But on the right, well, that's the reality. The second our data hits the real world, whether it's through a wire or just the air, it starts getting mangled by all that noise. So what's doing all this damage? Well, our data basically has three big enemies. First up is additive noise. That's just the random static, the thermal hiss that comes from, well, all electronics. Then you've got distortion. This is when the pathway itself, maybe an old phone line, actually warps the signal. And last but not least, interference. Think of it like crosstalk, where other signals and nearby wires literally bleed over and mess with ours. Okay, so how do we even begin to send our little hello through that gauntlet? The very first step is all about being efficient. We have to pack it for the trip, and I mean pack it tight. The fancy term for this is source coding, but you and I, we just call it data compression. It's basically the art of saying the same thing but with way fewer words, or in this case, fewer bits. You know, brilliant folks like Ziv and Lempel came up with these genius algorithms that are just masters at finding patterns and shrinking data down. And the suitcase analogy? It's perfect. Seriously, it's just like that. You don't just chuck your clothes into a bag, right? No, you fold them, you roll them, you try to use every last bit of space. That's exactly what compression is doing, making the file smaller so the journey is faster and easier. All right, so our data is packed up nice and small, but it's still, vulnerable. Those enemies we talked about are still out there. So the next step is absolutely critical. We've got to give it some armor. And this armor has a name. Channel Encoding. But this isn't steel or anything like that. No, this armor is made of pure math. What we do is we cleverly add some extra, redundant bits to the data. Now, these extra bits aren't new information. Think of them more like a super smart error checking system. And I want to be really clear here. This is not as simple as just sending the message twice. I mean, that would be a huge waste of space. No, this mathematical armor is way smarter. It's designed to anticipate the kind of damage that might happen along the way, and it carries the instructions to fix it. It's genius. You know, the very idea that you could get perfect error-free communication over a noisy, messy channel, that was completely revolutionary. And it all came from this guy, Claude Shannon, basically the father of information theory. Back in 1948, he proved with math that this wasn't just a fantasy. It was actually possible. And he boiled it all down to this elegant, simple little formula. R has to be less than C. So what does that mean? Well, R is your data rate, how fast you're sending stuff, and C is the channel's capacity, the absolute maximum speed limit of that specific pathway. Shannon proved that as long as you stay under that speed limit, you can use that clever mathematical armor to get your message there perfectly, every single time. So let's recap. Our data is compressed, it's armored up, now it's ready for the most treacherous part of the whole trip, actually traveling through the physical world. But here's the thing, it can't just go. It needs a vehicle, it needs a ride. I mean, think about it, a 1 or a 0. That's just an idea, right? It's not a physical object that can fly. So to actually travel, these bits have to hitch a ride on something physical, like an analog radio wave. And this whole process of getting the digital info onto that analog wave, that's called modulation. And there isn't just one road for this either. There are entire superhighways on the electromagnetic spectrum. You know your AM radio? That's cruising along in the medium frequency band. But your Wi-Fi, your satellite TV, that's all happening way up in the super high frequency band, which is like a massive multi-lane freeway that can handle way more traffic. I mean, data. But just like real highways, each one has its own kind of traffic jam. The low frequencies can get all messed up by atmospheric noise, from thunderstorms and stuff. The super high frequencies, they can literally get blocked by a heavy downpour. It's a real thing called rain fade. And even if you're on a wire, you've still got to worry about that crosstalk from the lane next to you. Engineers have to plan for all of this. So, after battling through all that noise, distortion, and interference, our signal finally makes it. It arrives, but it's still a mess. It's corrupted, it's riding on a wave, it's wearing armor, and it's all packed up. Now it's time for the grand finale, the unpacking. Basically, the receiver just does everything we just did, but in reverse. Step 1, demodulation. That's getting the data off the radio wave. Step 2, channel decoding. The armor is checked for any damage, the math does its magic to fix any errors, and then the armor comes off. Step 3, source decoding. The data gets unpacked from its tiny, compressed form. And then, at the very end of it all, there it is, our original message, hello, perfectly intact. Okay, now here's the part that's going to blow your mind. This whole journey we just walked through, the packing, the armoring, the ride, the unpacking, that whole complex dance, it doesn't just happen once. For you to watch a single video on your phone, this has to happen billions of times, every single second. And it has to be basically flawless. So if there's one big idea to walk away with, it's this. Our connected digital world, it isn't built on perfect wires and perfect signals. It can't be. The real world is just too messy and noisy for that. Inside, our entire modern life is built on a foundation of absolutely brilliant mathematics that takes all that chaos and creates perfection out of it. It kind of makes you look at things differently, doesn't it? This is just one of these incredible, invisible systems that runs our world. So what else is out there? What other amazing systems, all powered by clever math and engineering, are hiding in plain sight, just making your everyday life possible?